Yogah Karmasu Kaushalam.
I am Dr. Sanjeev Gupta from Sanjeev College, Ahmedabad. I'm going to deliver two talk. One will be on electric dipole moment, and another is magnetic dipole moment, and there are various applications. So basically, the plan of my talk is like I will start with the introductory part, where I will more concerned about the electric dipole moment and magnetic dipole moment, and then I will discuss about different applications. I'm going to use very famous two books, that is the J.D. Jackson by Classical Electrodynamics and D.J. Griffith Introduction to Electrodynamics. So before I start, I say something. One thing very important: the definition of both dipole moment. The electric dipole moment is a measure of the separation of positive and negative electrical charges within a system. That is a measure of the system overall polarity. If I take the SI unit, it is Coulomb meter, and also dY meter is another unit in physics and chemistry. Another topic is magnetic dipole moment. Magnetic north pole or magnetic south pole, which is separated by a smaller distance, then magnetic dipole moment have a dimension of current times area or energy divided by magnetic flux density. Its unit is ampere square meter. And these two topics are very important for different purposes. I will focus later on what are the various applications. But before, I'm going to start with very important uh, subject. This is the subject of radiation. So before I start direct electric and magnetic dipole, one should know what is the radiation. We can say if charge accelerate, their field can transport energy inversely out to infinity. So this is just the picture which indicates, and then that radiation basically known as what we are going to study. So let us assume the source is localized near the origin, and we are interested to calculate the radiating energy at time t is equal to t0. But we know that the power passing through its surface is the integral of the Poynting vector, which is I have written p rt, and the integrate close integral s dot dA, and of, later on s is nothing but the E cross B, and we know that electromagnetic wave travels at the speed of light. So therefore, this energy actually left the source at the earlier time, which is t is equal to t0, and which can I can write t minus r by c. So therefore, power radiated we can calculate at time t is equal to t0. So that is, this is equal to the limit of r tending towards infinity and the power at r and t plus r, t0 plus r by c. So this is general concept of radiation. So this on this concept of radiation we have three steps. The first step is, first we are going to calculate energy radiated by an oscillating electric or magnetic dipole, which is determined by the Poynting vector. So therefore that expression, this expression you may write as a 1. Once you know that S, then you can calculate the intensity which is obtained by the averaging over in time a complete cycle. So it means you have to calculate the average per hour to get the intensity. So this is the average calculation. Now third is very very important. Once you know the average of intensity, then just to integrate this average over a sphere of radius r. So this average and then integrate over dA, where dA is nothing but r square sine theta d theta d phi, where theta is ranging from 0 to pi and phi is ranging from 0 to 2 pi. So now using this concept, I'm going to explain much more for the electric dipole radiation. This picture, if you see here, which is this one, two tiny charge sphere, one having positive charge and another having negative charge with time t. And suppose we said that we derive the charge back and forth through this wire from one end to other with angular frequency omega, then we can calculate how much power it radiate. So for that, you can see this expression can derive using the concept of charge, and charge can be write q0 cos omega t, because this is oscillating electric dipole. So therefore charge is also oscillating. For oscillating electric dipole, the similar relation we can write Pt is equal to P0 cos omega t, and because we are working on z axis, so therefore that is the electric dipole at the z direction. Now I'm going to use 10th class mathematics. So you can see this is my midpoint, this is my positive charge, this is my negative charge. So and here P is my observer. So minus Q to P distance is denoted with R minus, and positive Q distance towards P denoted by R plus. And from origin it shows only R, which is making angle theta. So using the cosine law, that R plus or minus is equal to R root over 1 minus plus d by r cos theta plus d upon 2r cos theta का whole square. So therefore we can have the system having two charge. So therefore we can always write a retarded potential VRT in terms of one towards positive radius and one towards the negative radius. So therefore the expression 4 is my retarded potential. But we know that for a perfect dipole, I have put it down in last. You will ask some MCQ question. So you can see here for perfect dipole, we have a condition D should be less than R. It means suppose you have two charge, that positive charge and negative charge. So D is very smaller as compared to the R, that distance from the observer. So this is what we 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 are we are knowing this. Now equation 3, if I am solving question 3, this one in more depth, so I can take it out R comma, and then I can write this way minus 1 minus plus d by r cos theta d upon 2r ka whole square. But you know that d r by r is very small, so therefore this whole square is very very small and equivalent towards 0, so these terms can be neglected. So now you can see here the r plus minus is equal to r 1 minus plus d by r cos theta 1 by 2. Now we can use the binomial theorem, and binomial theorem is having this form So therefore, I have equation number 5. I can write R plus minus is equal to R 1 minus plus d by 2R cos theta. So this is my expression number 5. Now, again, I'm going to simplify this expression. If you look here, this cos omega t minus R plus either minus by C. So for that, what I'm going to do, I'm going to put R plus or minus value, that is expression number 5 in here. So I will have two terms, that is a cos C and cos uh, C plus D or C minus D. So we have a formula cos C plus cos D minus sin C plus sin D. I'm going to use this formula. When I use this formula, so I will get this expression. So once I have this expression, then you can see this terms omega d by 2c cos theta and this term going to change, because for perfect dipole moment we have to follow three conditions. D should be lesser than R, and D is lesser than R. We can write C by omega, and C by omega, we have a relation is lambda is equal to 2 by C by omega. So C by omega can be changed to lambda upon 2 pi. So therefore, D is very small as compared to lambda. So it means your wavelength should be very high as compared to D. So using this concept, what I am doing here, I'm putting here the cos theta will be 1, sin theta will be theta. So we can use this concept. So sin theta becomes theta and cos whatever theta becomes 1. When I'm putting this expression number 6, then you can see I am getting equation number 7, and equation number 7 you can have this way. So once you know the equation number 7, you can just put in equation number 4, what we have the retarded potential. So then you can calculate the retarded potential. So retarded potential you can solve, but you can see here one is negative and another is positive in lower side. So what you can do, you can take a like a LCM. So that becomes 1 minus d square upon 4r square cos theta, and these terms due to the dipole, perfect dipole, it becomes 0. So only 1 remains. And further, you can see just rearrangement the equations, and some common terms will be cancelled out, and then you can see here I am getting the last term, that q0 upon 4 pi epsilon r d by r cos theta cos omega t minus rc minus omega d 2 by rc cos square theta sin t minus r by c, and that becomes a perfect. Now I'm going to use the perfect dipole condition again. D should be very very small as compared to r. So once I use this condition, I will have this this expression where you can see here the d and the cos theta divided by r term is common. When I do the common terms out, so minus omega by c sin omega t minus r by c plus 1 by r cos omega t minus r by c. So you can see that our expression can have this kind of expression by 1 by r dependent kind of expression I'm getting. Let's say another multiple choice question. Suppose I'm putting a limit, that is limit is omega tends to 0, that is called static limit. If we put this limit, it becomes the potential is stationary dipole. So what happened when you put this expression, this first term goes to 0, then second term you should have only 1 by r. So that 1 by r becomes out, and q0 d is become p0. So you should have this the expression what you learn in standard 11 12. It means the field that survive at large distance from the source, that is a radiation zone. Now we are focused on that, all study on this zone, that is a popularly known as radiation zone. And that radiation zone, it means that R becomes larger than C by omega. So R becomes greater than lambda. So lambda is you can see is between d and small r. So my question number 8, what we are saying that expression, it becomes change for dipole approximation. So what happened? That whole term goes to 0. So why I should have another v r theta t, that's the minus p0 omega upon 4 pi epsilon c cos theta divided by r sine omega t minus r by c. That is expression. And this is simple, what we already know, that is the scalar potential we find out. So this is a scalar potential. Now, because I'm talking the z axis, and you have a charge, due to charge is passing with respect to time, so there is a current. So always we can write this expression. So we know that q is nothing but the q0 cos omega t, because this is oscillating charge. So always we have that current in terms of sine omega t and z axis. Now we can write the vector potential, the mu 0 upon 4 pi integration minus d by 2 to positive d by 2, and then you can write dz upon r. So once you put these all things, you will get that vector potential a r t theta t in terms of minus mu 0 p0 omega 4 pi r sine omega t minus r by c is z axis. So you can see that equation number 8 and 11, these we have calculated, and these are scalar and vector potential respectively. Now our aim to compute the fields. So for that, this is a well-known expression that del V in terms of dou V upon dou R in a spherical coordinate, and these are Lorentz condition. You can see these two Lorentz condition where you can get electric field and magnetic field. And del V you can calculate from here for a spherical case. So what we do, we know V, we know A. Now question comes to calculate E cross B. That's very simple. So for that, del V can be write dou B upon dou R, 1 upon R, dou B upon dou theta in spherical. So once you put these things, you can see here minus, you can see for perfect dipole moment and radiation zone. So you will get the equation number 13, that P0 omega square upon 4 pi epsilon c square cos theta divided by r cos omega t minus r by c. This is expression. Dou del v we have calculated. Now we can also calculate del A upon del t. So del upon del t is nothing but the whatever you have A vector potential, just differentiate with respect to t, but z you have to calculate in terms of the spherical coordinate. So what I am doing here, I am putting in the spherical coordinate. So we calculated del A upon del t minus mu 0 p0 omega square 4 pi r cos omega t minus r by c cos theta r minus sin theta d theta. Now you can calculate Lorentz condition. We put the Lorentz condition. So del minus del v, we have put it down this expression, and minus del a upon del t using equation number 14. These are equation number 14. So this, you can see this common term cancel out, and you should have that electric field is equal to minus mu 0 p0 omega square upon 4 pi sine theta divided by r cos omega t minus r by c. That is a theta dependent. The field becomes this theta dependent. Now come to the calculate the magnetic field. So del by A, and for del by A we can write in terms of 1 by R dou by dou R a theta minus dou by AR upon dou by d theta and phi dependent. So once you put everything, you can see here this is the AR term, this is the A theta terms, and just differentiate and follow this my calculation, and then you can see here you are getting for radiation zone that beta, that B magnetic field is you are getting minus mu 0 p 0 omega 0 omega square 4 pi c sine theta by r cos omega t minus r, and that is a phi dependent. If you look equation number 16, that is the previous one, that is for electric field, and this is for magnetic field, for equation number 17. And then there is another question comes in mind. If you have electric field and magnetic field, can you calculate? And the the average, that was my second point. So our aim was to calculate first S. S is my using the pointing vector 1 upon mu 0 E cross B, and you can r theta and phi you can take into cyclic order. So theta, if you multiply with phi, you will get the r component. So 1 upon mu 0, that the first electric field component and this magnetic field component. So only because these are both are same, so it becomes square, but theta and phi will you will get the r cap. So S becomes this whole terms. Now you have to calculate the average over a complete cycle, as I said for second step. So for that, you need to take care of omega, that cos square omega. This because this is a kind of for the complete cycle, it will give the value. This is half. So you will have half the 16 multiplied by 1 upon 2, that will 32. Now I'm going to use a third step, calculate total power radiated. This is nothing but the total power is capital P integration S dot dA, where dA is nothing but the r square sine theta d phi, and my integration is running from for theta is running from 0 to pi and phi is running from 0 to 2 pi. So 0 to 2 pi it comes directly, and sine theta and sine square theta it becomes sine cube theta, starting from 0 to pi. If you solve, it will give 4 by 3. Once you put the expression, you will get that power, total power radiation is mu 0, P0 square omega to power 4, 12 pi C. So it is very remarkable things that capital, that P is directly depend upon the P0, P square, and also omega to power 4. So this thing always remember. We will later on we will discuss more, and this expression basically once you have omega p0, then you can calculate how much power it radiates. So for using this formula you can calculate electric dipole moment. So for this, what I have done, we have considered a wire having a loop kind of wire which has radius b, and around which we derive an alternative current. So you can see here that current IT is equal to I0 cos omega t. So why I have taken, because this is the oscillating uh, current, and figure I'm going to describe you very shortly. You can see this is a loop, and this z axis, and this is y axis. Again, you can see the observer is here at P point. The from origin of this loop to observer having distance is r, and this vector B is making a vector, that is a V vector, and the V vector is also making the different notation of r, and where you can say the angle between this r vector and the B vector is psi, and z direction, and r having making theta angle. and this is the x-axis. But you can see here very shortly. You can see here this direction, because this is B, and this also we call it B cos phi angle, because this angle is phi dash. Why phi dash I will tell you later on. But you can see here the angle between x-axis and b-axis, and this is horizontal component, so that we call it b cos phi. And if you take the vertical component, so that in y direction we call it b sin phi. Let's say, suppose you have a two vector. I'm just talking about the trigonometry, and you have phi angle. One is r and another is B. So if you have these two kind of things, so always we can write R dot B, and that is RB cos phi. So what this is what I have written. So I have collected very much information regarding this loop. So we can derive our scalar and vector potential. So for that, equation number one I have written for the oscillating alternating current. But this is a oscillating magnetic dipole, so therefore that MT is nothing but the area multiplied by the current which is flowing in the z direction, which we noted by equation number 2. So you can see area, suppose you take loop and having that vector v or radius b, so it goes from here to here, it create area. This area is pi b square, and the current is I. So in z direction. So what we have written here, but we know that it is can be written as I0 cos omega t in z direction. So therefore, if I write the expression for oscillating magnetic dipole, so I can write that mt is equal to m0 cos omega t z, which is acting on z direction, which is my expression number 3, where m naught or m0 is equal to pi b square I naught. So this expression where we can write. But important thing is that because there is a very important concept, because the loop is uncharged. When the loop is uncharged, so it means the scalar potential is zero. So therefore, you can see that my phi RT becomes zero. So only we have a retarded vector potential. So therefore, we are going to write a retarded vector potential, which is the form of A RT, that is the mu 0 upon 4 pi 0 to 2 pi, because it is starting from here 0 and it goes to pi and then come to the 2 pi. It's full loop, it goes from 0 to 2 pi. So therefore we have taken 0 to 2 pi, and then therefore that I0 cos omega t minus r by c, and that is another the the current terms di. But di is always we can write, because di prime is nothing but the what we have shown in the earlier, that is nothing but the our what we have calculated dot r dot p r dot b is equal to rb cos phi in the terms of rb cos phi. So you can see here that if angle is phi, so we can write di along z, but it is not z, because it is going the radial direction. So di prime can be written as b cos phi prime d phi, and is moving on y axis. So putting all things, all those values, you can see here, that comes to the question number 5. Equation number that is 5. Y is outside. So here you can say this phi term, phi dash and phi dash comes. Now we just you can see I have taken some part of my loops. So this is a R, this is a another R, and this B, making angle phi using the law of cosine. Then what happened that R is equal to under root R square plus B square minus 2RB cos phi, which is I have written. But if I distribute the angle in different way, so you can say that B sin phi and R B cos phi we have given. If we distribute that R, this R, so R, you can have two components. There's vertically, that is R cos theta, and sorry, horizontally it is R cos theta, and vertically this is R sin theta. So you can say in x direction you will have this B cos phi and R sin phi, R sin theta, and and if you look in y and z direction, you can feel r cos theta and b sin theta. Therefore, we can have two two vector, that is r vector. You can write r sin theta, that is the x direction, plus r cos theta in z direction. Even though b component, we can write b cos phi dash x direction plus b sin phi dash in y direction. So therefore, we have a two equation. Now, what we do, we can take the dot product. So what I have done, I have taken the dot product r dot b. So therefore, rb sin theta and cos phi plus rb cos cos theta, or you can say cos theta. This is cos theta and sin phi. So you can see that rb rb uh, rb Yeah, r dot b is equal to rb sin theta cos phi. Cos phi it means this term is goes to zero, I suppose. So we can write always, we can write always so we can write always that cos phi in terms of sin theta and cos phi. So we got this equation number 7. Now what we will do, equation number 7, we put in equation number 6 what we have, that cosine law. So instead of we are putting cos phi, we are putting some another things. You can see here that sine theta cos phi. Now again, this is a multiple choice question. We can ask in the last in MCQ in your exam. So if I take the perfect dipole moment, so for perfect dipole moment, the condition should like that loop has to be extremely small. It means the b value, like when you take this v value, it should be very very small as compared to what we have taken the r value. So it should be small, so it should like a dot. So it should be very very small as compared to the r. When I put these things, so you can say when I taken r out, so this is a 1 plus b square I r squared minus 2 br sin theta cos phi. Now again, so this is small, so that's why we neglected this. Now we have a r 1 minus 2 br sin theta cos phi, and then 1 by half. Then now again use the binomial theorem that 1 half goes inside, and then you will get this expression r is equal to small r 1 minus, and then b by r sine theta cos phi prime, and therefore we can always write 1 upon r is equal to 1 by small r 1 plus b by r sine theta cos phi prime. So therefore you can write cos omega t minus r by c, always write this way. I'm putting this r values, so you can see here. this expression. So this multiplied with this, and this goes divided by this r by r cancel out. That b by c sine theta cos phi prime. Now you can see here that is cos c and d. Then again you have a cos c plus d form. So we know that cos c plus d is nothing but the cos c cos d minus sin c sin d. Then again, I'm opening this bracket. If you look at cos omega t minus r by c, and that cos omega b c sin theta cos phi prime minus sin omega t minus r by c sin omega b by c sin theta cos phi dash. But we know that if the dipole is very very small as compared to the wavelength which we radiated. So what does mean by, so it means, so b is very very small as compared to lambda, and lambda is nothing but the c by omega. So when it happens, it means omega is omega by c, that or vice versa, c by omega is very very small. So we can neglect this term. So ultimately, you can see here thus omega t minus r by c. We can write omega cos omega t minus r by c minus omega b upon c sin theta cos phi dash sin omega t minus r by c. That's equation number 10. Now this cos omega values, I'm putting the expression number 5 in equation number 5 where it demand. So after putting this, you can see that vector potential ART becomes mu 0 I 0 B upon 4 pi y direction 0 to 2 pi, that cos omega t minus r by c minus of omega b c sin theta cos phi dash sin omega t minus r by c, and then you have a cos phi angle and d phi angle, and of course you have a one, that r component, that is 1 by r, and bracket 1 plus b by r sin theta cos phi dash. After solving this, if you solve this, then you will have mu 0 I 0 b y component 4 by and 0 to 2 pi, then cos phi cos omega t minus r by c omega b by c sin theta cos phi sin omega t minus r by c, plus you have another component of this plus b by r sin theta cos square phi minus omega b square r by c sin square theta cos cube phi sin omega t minus r by c, and you have a d phi prime. So once you have all this, then we can use always identity. Once you have a cos phi term with d phi, it is running from 0 to 2 pi, it always gives you 0. And another, if you have 0 to 2 pi, if it is a square of cos square phi d phi, it always gives pi. So I'm going to use this identity, and we get the expression number 11. You can see here that a r theta t, this is nothing but the mu 0 m0 4 pi sin theta by r 1 by r cos omega t minus r by c minus omega c sin omega t minus r by c, and that is a psi dependent. So moving ahead, we now we get the vector potential. uh, you can see here I have written here. Now we can look this for the static limit, as we have already done for electric dipole radiation. We have checked for a static limit. So this expression number 11 for a static limit, you can say that omega is 0 tending towards 0. So what happened, that r becomes very large as compared to c by omega. So what happened? So this terms goes to out, but this terms only you will have only 1 by r dependent. So that only 1 by r, that is r. So this is r square. So That MCQ, you will have the expression that A R theta D is vector potential is directly correlated with the mu zero m0 upon 4 pi sine theta by r square. This is expression number 12. Now, again, if I look more in depth with equation number 11 for the radiation zone, if I look for the radiation zone, it means R is very larger. R is larger than C by omega. If I put this, then I can write that A R theta and T, that mu 0 m 0 upon 4 pi sine theta by R, then that the terms of this term is goes to zero only. You will have this term, and this I can write here, and that is a phi dependent. So lastly, you can see I get finally the vector potential in terms of mu 0 m 0 omega upon 4 pi c sine theta by r sine omega t minus r by c, and that is a phi dependent. So this is equation number 12, which indicate I have a vector potential. And we know that scalar potential is zero. Now we can use Lorentz condition. So Lorentz condition says that if you have a del, because we don't have V, so always you can say this terms goes to zero. So you have only this terms. It means electric field can be calculated when you differentiate with respect to time. So what I have done, just taken the equation number 11, sorry 12. So this is 12. I just differentiate with respect to time. When I did this differentiation, then you can say that all terms here, that mu 0 m 0 omega square of 4 pi c sine theta by r cos omega t minus r by c, that phi dependent and phi direction. Now we are going to calculate the magnetic field. Magnetic field is simply, I can write that is a del cross A. So we know A. So just I have to multiply del and whatever A I have written here. But del is only here is R dependent, because only this R we have. But we know that if we have R component and phi component, so I will always give a theta negative component. That we know because this is a cyclic order. So simply I multiplied this way with R, and this you can see here I'm getting here only the theta, but in the case of minus sign, and that c is all extra c will come here, that is c square, because it is differentiate with r sine theta by r cos omega, because it convert to the cos omega t minus r by c, and you can say this is a theta dependent. So it means, so magnetic field is theta dependent, electric field is phi dependent. So these two things always remember. Now my problem is little bit solved. Why solve? Because I know the electric field, the magnetic field. Now we can take care of lecture one, the method what I said. So the first step, I need to calculate the energy flux for magnetic dipole radiation. That is a simple using the Poynting vector theorem. So 1 upon mu 0 E cross B, but we know E. So 1 upon mu 0, I take it out. So I have put it down electric field, and then you can say I have put it down the magnetic field. Both are multiplied. Only just I have to consider that phi and theta always give you the R component. So you can see here I have this expression. But if you remember, when I do the average over full cycle, that cos value will give me the half. So the second step for the intensity, so this average S, I have calculated this whole thing. Just put 1 by half and the R component. So this is my equation number 16. Now the third step, to calculate total power radiation. And total power radiation, it means this P is nothing but the integrate the average S dot dA. dA I know that is the R square sine theta d phi. Just I am putting in this equation. So you can say that d theta phi, your theta is running from 0 to pi, and phi is running from 0 to 2 pi. So you can say here it comes 2 pi, and 0 to 2 pi is the sine cube theta, and sine cube theta always give me 4 by 3. So once you put all values, then you can see that magnetic field dipole, that that total power radiation due to the magnetic dipole radiation, due to dipole magnetic dipole, what I'm getting, that mu 0 m0 naught square omega omega power 4 divided by 12 pi c q, that is r dependent. So finally I am getting the expression for magnetic dipole radiation. Now you can always have a MCQ type question like that. P, due to the magnetic dipole radiation, this omega power 4, and that always m0 naught power 2. So it means that is the intensity. If I make the intensity profile, it has a shape of donut, and like donut means you have this of this of shape, and it radiated it radiate power like omega power 4. Always remember, this is MCQ type question. And the important thing is that what I'm going to do, I'm just comparing both my that total power radiation, how the expression is valid, and what is the ratio behind that. So you can see here that here I have written the total power radiated by the magnetic field, total power radiated by the electric dipole. So you can see this expression, and you can see this expression. So finally, you will common things you can cancel out. Finally, you can have that m0 square divided by c square p0 square, and here you can always write that m0 p0 c ka whole square, and therefore that p magnetic, you can always write that p electric times that m0 p0 c, and the whole thing by square. So if I take a, for example, if I take something like you have a magnetic moment like pi b square I0, and p square p0 is nothing but the q0d, and I0 is nothing but the q0 omega, and d is something pi b. If I put all things inside this expression, then you can see always that magnetic and electric total power radiation ratio, I'm getting b omega by c ka whole square. So so what does mean by, so that means always remember that electric dipole radiation always dominate, always. So magnetic dipole having very lesser amount, but electric dipole radiation has, which is higher value, which dominate if we compare with the electric and magnetic both cases. So uh, these are few understanding and the comparison with electric and magnetic. I hope you have seen. Now for the sake of city, I have taken few cases, just you can look out. uh, let's say a square loop having area is A, lies in x and y plane, and which having electromagnetic wave is equal to that is equal to E0 cos k dot r omega t, is propagating in a space. The power crossing through the square loop we need to calculate. So we always know that E is equal to E0 cos k dot r omega t. So once we can always calculate B, which is nothing but k by c, and that is always in terms of E0 cos k dot r omega t, and you can write P is equal to A, that is the A dot 1 upon mu 0 E cross B. So A dot mu 0, where you can multiply both expression. And once you multiply with both expression, you can see E0, KE0, and then that average of this is half. That half you can take it out, and then that becomes KA0, and then this half becomes 2, that mu 0 c, and this it becomes E square, and K is making angle with A. So the total power radiation is something nothing but the 1 upon 2 mu 0 c E 0 square and A dot K. So that therefore we have always just do the trigonometry and you can find out this. So we have so many the homework for you. You can do in whenever you have time, like an electric dipole having dipole moment of magnitude p is rotating about an axis, passes through its midpoint and perpendicular to p. You have to calculate the power radiated by dipole. Another example is, suppose you have a dipole moment which is amplitude p0 in terms of charge, that is a q, and acceleration is a of accelerated charge is, the equation of motion of accelerated charge is sinusoidally varying electric field, find power radiated. So I have given some exercise to you. You go through it and try to understand both things. Once you understand the electric, what is the electric dipole moment, what is the magnetic dipole moment, and then you can have idea how that these these are important. So you can look for the bigger cases, like you can use this concept to just look out the satellite communication, and this very vast area for satellite communication, because nowadays you can see that ISRO and DRDO and many other NASA, so many other uh, funded projects are coming out on where the satellite communication is very important, where the fundamental aspect is to calculate the total power radiation, to understand the electric and magnetic dipole moment. Even though once you know the idea about magnetic dipole moment for a revolving electron, so basically it gives the idea about the magnetization, how magnetization comes in picture. And this is a very always a vast area. If you take the nanotechnology in this case, and if you prepare any magnetic nanoparticle, it is always a fascinating area to understand the magnetic dipole moment for magnetization case. Different antennas, I have not talked antennas case, but actually I thought I will give you some idea about linear antenna, half wave antenna, because this antenna is directly based on the that electric dipole moment concept simply. And you can just, this is extension of the electric dipole moment. So you can calculate what is the radiation pressure. You can calculate many different properties of antennas. Even that, if you tune the transition on electric and magnetic dipole moment, so you can calculate different kind of doping in bulk structure or nanostructures. So so this is also very very important for the material properties, as per new research is going on. Further is very very important now, the spin dynamics. Spin dynamics is totally depend upon this you can see there is storage, SSD is coming out, the hard drive earlier, 10-year back, the hard drive, you can imagine the floppy size. Now the, you can say the pen drive size is going to reduce. So spin dynamics always create a kind of a new picture, and it has a new dimension towards research, and people can go in depth to understand how the spin dynamics is important. Different motors also basically we can say uses the concept of electric and magnetic dipole movement. So this list I have given just to showcase to you, but there are plenty of application of electric and magnetic dipole movement. So I'm just stopping here, and I just give you best of luck and best wishes. And but I always acknowledge my fundings. Uh, I must acknowledge Professor P. N. Gajjar, Professor Jha, Professor Arora, and so many other respected professors who always help me, and different funding agencies, DST, Fulbright, St. Xavier College, Ahmedabad, and uh, Indonesia project. And thank you everyone, and thank